Hey, and welcome back to Probably Optimal. In the last video we have started to talk about the probability space omega AP and in particular about the sample space omega. And in today's video we will talk about the next ingredient, the so-called probability measure P. But before we can do that, we will first have to look at so-called measures. To give you an intuition for the definition, I have 3 examples from everyday life. So, first imagine that you want to find the length of a wall. How do you do that? Probably you just go and get your measuring stick. But what do you do if this measuring stick is actually shorter than the wall? Probably you simply split the wall into 2 parts. Measure the length of the first part and note it down somewhere. Then you measure the length of the second part and note it down, and finally you simply add the corresponding values. Or imagine that you have an apartment and you want to find the area of it. What do you do if it has a weird shape for which you do not know an easy formula? Probably you try to split the total area into separate simpler parts for which you can find the area easily, and then you add up the corresponding values. That is, the area of the whole apartment is given by the sum of the areas of each single room. Finally, imagine that you are looking at a nice statue and you are wondering about the volume or maybe the weight of that statue. As before, you can find that value by splitting the statue into separate parts, measure the volume or weight of each one of these, and then add them up. And in this case, these 2 values are actually also very related, because you can translate between them. If you additionally know the density of each material, you can compute the weight by multiplying the volume by the corresponding density. Okay, so how do mathematicians define a measure? First of all, you need to have a measurable space x sigma. That means that you need to have a set x and the corresponding sigma-algebra on that set. This is the wall, the apartment, or the statue, and their corresponding measurable sets. Then, a function mu from sigma to the positive extended real numbers is called a measure if it satisfies 2 things. First, it should assign the value 0 to the empty set. That is, the length, the area, the volume of nothing should be 0. And second, if you can decompose your set into at most countably many disjoint sets, then the value assigned to the whole set is given by the sum of the values of its parts. That is, the length of the wall is given by the length of part 1 plus the length of part 2, and the area of the apartment is given by the sum of the areas of each single room, and so forth. Here, the first condition is basically our only option to have a good definition, and the second condition is called sigma-additivity, just in case you haven't heard that before. Okay, so that's the definition of a measure. And what is a probability measure? Here we only have to impose one further condition, which is that the measure should be normalized. That is, the value that is assigned to the whole space is 1. That's the only difference. So, what does it mean? It means that a probability measure measures everything in relation to the whole space. And this actually gives us a general recipe to construct probability measures. If we have a finite positive measure mu on our space omega, we can get a probability measure p from that by simply normalizing mu by mu of omega, which is the so-called normalization constant. And this tells us that the probability of an event A is simply the fraction of the total weight that is captured by A in terms of the measure mu. To make that clear, I have 2 simple gambling situations. First, as always, coin tossing. We have seen in the last video that if we toss a coin, we can define the sample space omega as the tuple 0, 1. Now, if our coin is fair, we typically mean by that both sides are equally likely, so that the probability for each side is 1/2. But why? For this, simply take a measure that assigns the same weight x to 0 and to 1. Then, by using the additivity from before, we find that the total weight of omega is given by the sum of the weight of 0 and 1, which is 2x. So if we take our general recipe, we find that the probability of 0 is simply the weight of 0 divided by the weight of the whole space, which is x divided by 2x, or simply 1/2. And in the same way, we find that the probability of 1 is also 1/2. But what changes if our coin is not fair? In this case, we'd have to distinguish between the weight assigned to 0 and the weight assigned to 1. This would then tell us that the weight of the total space is given by x plus y, such that the probability of 0 turns into x divided by x plus y, and the probability of 1 to y divided by x plus y. So while the values change, the recipe stays the same. As second example, let's consider the rolling of a die. In the last video, we have seen that the sample space is given by the numbers 1 to 6. And if we again assume that the die is a fair die, then this would mean that we assign the same weight x to each of these outcomes. Then, by using again the additivity here, we find that the weight of the sample space omega is given by the sum of the weights of each of these outcomes, which is simply 6 times x. Therefore, if we now apply our general recipe, we find that the probability of each single outcome is x divided by 6x, or simply 1/6. As before, you could find the probabilities for an unfair die, but I will stop here because this would get too messy for YouTube, I guess. So that's it for the video. I hope I could provide you with some intuition for measures and probability measures, and thanks for watching.